All right, it is now 3:30. Welcome back, everybody. Thank you for staying with us till the end of the day. We have our last but not least talk of the day by Flora Wang. I'm very excited to introduce Flora because we actually graduated from McAllister and was actually both, we were both math majors at McAllister. So this is really exciting to be able to be here with you today, Flora. And Flora is currently a fellow at Insight Data Science. And today she's going to do a presentation on recurrent generative networks. So take it away.
Thanks. Thank you so much for the kind words, Kim. Yeah, my name is Flora, and I'm really happy to be here to be able to present work I did with some collaborators during my master program. So the topic here is recurrent generative model for multi-resolution satellite image. And oh wow, we have another Insight fellow. And yeah, this will be specifically for Cropland monitoring. Okay, I'll get started. So I want to just start by briefly talking about why cropland monitoring is important. First of all, agriculture resources are witnessing tremendous supply side stress as a result of increasing population, suboptimal farming practices, and also climate change, as well as human activities such as urbanization. And automated cropland monitoring can really help us ensure crop production will be scaled up with the growing population in the right places and from the environmental perspective. So then for the data that's being used for cropland monitoring, we are using the remote sensing image. And the recent advancement in collecting and processing satellite remote sensing data really make it possible to monitor land covers in large regions. And here I'm just listing a few most popular remote sensing data sources. Each of the data source has a specific spatial and temporal resolution. And in this project, we're using the first one called MinneWiADS and also the one called Sentinel here. So as you can see, they each have their own advantage and disadvantage. So for MinneWiADS, it's available on a daily basis. However, it's of a relatively low resolution. But with Sentinel, it's available on less frequent basis, but it has a much higher resolution for the in terms of compared to the MinneWiADS data. So in this project, we were really trying to build a framework to be able to combine the both data set and really utilize the best of the two worlds. So some challenges that we're facing when it comes to cropland monitoring is that we need to extract a temporal growing patterns from multi-temporal satellite data. And what that means is we really can't make the classification based on a single snapshot from a single date. And that has a lot to do with remote sensing data often contain a lot of noise. So on this image here, I'm showing a snapshot from one single day. And as you can see, there are lots of clouds. And when that translates to the data science, it just means there will be missingness in the data. So with that, most existing sequential model have shown success only on coarse resolution data. Like MinneWiADS is available on a daily basis. So that really provides a way to handle the noise because you can just create composite by aggregating data from multiple dates and by selecting the data with the least noises. But these coarse resolution data set would be suitable for monitoring small scale farms that are quite common in many parts of the world. And those small farms, we really want to use the high resolution data sources like the Sentinel or Landsat, but again, they are available on much less basis. So just to summarize, the major issue with remote sensing image is often has missingness or of poor quality due to clouds. And by if we create composite images, it will really result in infrequent data, making it very difficult to capture the temporal patterns. So now I want framework that we are proposing. So basically, first we want to use a sequential generative model to capture the distribution of the high-resolution data. And then we want to use another sequential generative model to capture the distribution of the multi-temporal data. And more specifically, we want to use the temporal pattern from the low resolution yet more frequently available data to guide the generative process of the high resolution but less frequent data. So now I want to give a overview of the variational recurrent neural network in a nutshell. This is the model that we're basing our framework upon. So this model is proposed by Wang and his student from 2015, and it's really a modification upon the vanilla recurrent neural network. So in the vanilla neural network, we have at each time step, we have an input state, a hidden state, and then the output state. And each hidden state is dependent upon the previous hidden state. And then it forms a chain. And that's also how recurrent neural network or its variant LSTM can remember many steps from the past. And then with the variational recurrent neural network is introducing an additional variable called Z, and Z is termed as the latent state, or you can view as a prior. So here, basically, then with the introduction of Z, we have 5 steps in total. So first, we have a prior generation, where we generate the current Z depending upon the previous hidden state. And then we have the generation of the input variable X, and X is dependent upon the current Z and the previous hidden state H. Then we have the recurrence relation like we had in the regular neural network. Here, the hidden state not only depends upon the current input and the previous hidden state, but also the current latent state. And then in the end, we have the posterior inference of Z, which is dependent upon X and previous hidden state. So in a more mathematical representation, Z and the X would be all sampled from a normal distribution just to keep things simple. And it will depend, and the mean and sigma here will be parameterized by neural network, and depending on the variables that I was previously mentioned. So why do we want to use variational recurrent neural network? It's because the crop growing process is often affected by environmental conditions like climate, soil type, or the slope of the land. And while recurrent neural network is deterministic, variational recurrent neural network has the stochasticity in it because of the sampling of the latent variable Z. So it allows us to better capture the variability due to the different environmental condition. So here, so our model is built upon variational recurrent neural network. And what's special about this about our approach is that we are actually using the hidden representation from the coarse resolution to guide the generative process of the high resolution. And what that means is for MinneWiADS, like I was showing in the previous slide, the generation process is a standard variational recurrent neural network where Z is dependent upon the previous hidden state and X, current state X. But for the higher resolution Sentinel, the Z is not only dependent upon the previous hidden state from Sentinel image, but also from the MinneWiADS image. So yeah, you can also see it from this graph here. And the idea, again, is because for MinneWiADS is more frequently available, so we can have a better representation of the temporal pattern. And after gathering the latent variables from the generative model, we use them to capture the progression of classification confidence over time. So we use accumulated information until time t, represented by OIT here, to make classification at time t. Then we compute a posterior probability of class label at time step t based on a softmax function. So in terms of the study setup, our study region covers 490,000 locations at the resolution of Sentinel data. And we established the mapping between MinneWiADS and Sentinel to gather the MinneWiADS data for each location. And in this particular study, we only consider 3 major crop types, which are corn, soybean, and sugar beets. And our data is fairly balanced, meaning that we have about 200,000 locations for corns, 100,000 for soybeans, and about 100,000 for sugar beets. So we can see that our method, here is the overview of the result. And for baseline, we did like random forest, forward convolutional neural network. And we also did the baseline LSTM with imputation. And we found a few things. First of all, that the Mars is our proposed solution, and it really performs the best in most cases. And also, in general, the sequential models such as LSTM perform much better than the static model like forward neural network or random forest. That's because the static model capture the temporal pattern very well. And also the solution based on variational recurrent neural network are better than the pure LSTM. For the validation, we did randomly select 60% of the data for training and tested on the remaining 40% of the data for each region. And for training and testing, they are sampled from the same region. So that's for the entire region test. And we also did a cross-region test where we select a continuous test region and take training sample that don't overlap with the test region. So here I'm presenting the classification confidence graph over time. So like I mentioned, in the model, we gradually update the discriminative knowledge that's denoted as OIT to capture the progression of classification confidence. And here we apply this model from April to November, and which include 23 time steps. And for each class, we're measuring the classification confidence over time. And our method shows that for corn, you can see there's a quick jump in terms of confidence at time step 8 and 9. And that corresponds to June 14th and June 24th. So to validate this, we show the RGB image on the example region captured upon June 24th. And we can see, so corn is highlighted here in yellow, and we can see that it really turns days compared to soy and sugar beet. So that means we're actually being right about gaining a more confident prediction at that time. So to reiterate, we proposed a probabilistic method that combines the temporal information at a coarse resolution and the spatial knowledge at a high resolution for crop detection. And our method shows that we successfully detect crops in large area and also leads to early detection results. And one side benefit that I didn't expand upon is it can also be applied to generate missingness. So it can be combined with like adversarial network to actually generate the missing data from the high resolution image. So for future direction, we can apply the proposed method on more land cover types or different type of data sources. But what's more important is this proposed method can also be extended to other domains, such as electronic health record, because they can also be from different time scale with different missing rates. Yeah, so that's all I have for the presentation. I think I went much faster than I thought.
Thank you so much. Oh no, that was a lot of information. Yeah, so as people, please feel free to ask any question for Flora.
Yeah, and I do have backup slides, so I can also talk a little bit more.
Well, you can, if you want to do that, we could do that because we still actually have 23 minutes.
Yeah, okay.
And before you do that, I do have a question, probably a little bit of a silly question.
Oh.
So, can you talk a little bit about the computational complexity from going from just a vanilla RNN to variational RNN?
Sure. So I might have a slide on that. I think it's the model training. Yeah. Yeah. So first of all, I don't think it will create much higher complexity because we are just introducing a latent variable, and for recurrent neural network, we have like basically 3 dimensions for the data. You have the feature dimension, you have the time step, and then you have the batch. This is going to be the same for the variational recurrent neural network. So here I said the time complexity for each iteration will be x and t, where x is the feature dimension, and I think n would be the hidden representation and the latent variable, and t would be the time step. Yeah, so basically there will be still the 3 dimension in terms of the complexity.
Thank you.
No problem. Yeah, so do you want me to talk a little bit more from the...
Yeah, I mean, why not? Because we still have time, and I find that well, we have one question coming in. So could you use data from previous years to improve early detection?
That's like, it depends on how early you want to predict, right? So you can definitely use data from previous years, and that's essentially what we are doing. So for each each current time step, we're using the historical data from the past. But I think there's a certain limitation on how far you can go back or go further into the future. So I think what we are showing here is with the classification confidences. At the early stage, you can't really be certain about your classification results. But as you're going closer to the current time step, then you're very confident about it. Yeah. Does that answer the question? Cool. So I can quickly talk about the data generation process that I skipped because I thought it might be too much information. So basically, the variational recurrent neural network can be combined with the adversarial data generation, where in our example for the Sentinel data, we had like missingness in between dates. So the challenge is how can we ensure the generated data will be consistent with the true values? And we can do that by applying a regularizer, adversarial regularizer, to inform that the generated data wouldn't deviate too much. So so basically we apply a regularizer so that when we're generating the missing data in between, it will be looking closely to the time step that we have the next available data. And so this is the adversarial loss, and it's again, yeah, just so it can. Let me see. So the cost function from the generative model will be combined with this regularized loss. So this loss would coming from the variational recurrent neural network. And then by adding this regularizer, we can ensure that the generated data will be close to the truly available data in the next step. And I can quickly show you the validation. So again, here we were generating data for July 24th to September 2nd, and using data that's before July 24th and after September 2nd. And we measure the generated data in terms of average distance with the true data. And as you can see, I think Mars, this is without the adversarial regularizer, and this one is with the regularizer. So this one is having a much better way. This red one is with regularizer. So yeah, so we are getting a better quality data by applying the regularizer. Yeah, so this is the detailed loss function from the variational recurrent neural network. Essentially it has the KL divergence and the expectation over the. So this is also called a elbow, evidence lower bound. But if you're interested, you can find the original formula from the variational recurrent neural network paper. And yeah, we're essentially rewriting this in terms of the low resolution and high resolution. Again, the only difference for the high resolution one is the latent space will be dependent upon the low resolution data. Are there any other questions? I'm happy to clarify. Yeah.
Can you talk a little bit more about other application, in addition to this one that you're talking about?
Sure. Yeah. So I think the application would be like, in general, when you have two different data sets that are available on two different scale, two different resolution, and maybe you also have missingness from one of the resolution, then you can use the information from more frequently available data to help you generate the less frequent data. So essentially, it's building a framework to work with two different type of data sets.
Thank you. And then we have a question from the chat. Do you have any problem with image registration?
Could you clarify what do you mean by image registration here?
Well, while San could from low to resolution to high resolution.
So you mean generating image from low resolution to high resolution? Yeah. So essentially, what the variational recurrent neural network is doing is, yeah, so maybe I should explain the slides a little bit more. So here, for MinneWiADS, we can see we have input and then hidden state, and hidden state is connected as from each hidden state at the current time step is dependent upon the previous time step. And then for the Sentinel, what's special is for the Z, for the latent space Z is dependent upon the current time step of MinneWiADS. So that's how we're passing the information from the low resolution data to the high resolution data from Z. Because later on, as I showed here, Z is using a Gaussian smoothing function, we're translating Z into the predictor, basically. So that's how we translate the information from low resolution to high resolution by allowing the latent variable to be dependent upon the low resolution data. Yeah.
Does that answer your question, San? And then we also have another question. Okay, awesome. We have another question from Sat too. Flora, can you elaborate on how you can use this method on electronic record files?
Yeah, so that's mentioned in the future direction, so we didn't think so deeply into that. But I imagine you can basically use this framework. Maybe you have some time series that are available on a more frequent basis, then you can you can build a recurrent neural network on that, and you extract the latent information from that time series. But then you have another time series that's available, maybe for different in electronic health record, I know for different measurement, they're taken on different time step, right? Some are taken more frequently, some are taken less frequently. So you can use this idea here to build basically a link between the two time steps, two time series, and you can infer the missing gaps for the less frequent data using the more frequently available data. Yeah, I think that's our idea.
Well, we have 10 minutes left. So if you have any questions about anything, feel free to. Yeah, I'm sure Flora is open to answering questions that's not deep learning related to. If you're curious about being a fellow at Insight or the master program at the University of Minnesota.
Yeah.
So we'll hang around until 4:10 here, but if you decide to drop off, make sure to come back at 4:10 in the stage area for as we wrap up the day, and then we'll also have networking session on Gather Town after. So stick around, get to know people, and we look forward to getting to know all of you. But yeah, we'll stick around here for a little while longer. So if you have any questions last minute or something, feel free to type in. This is really cool work. It's definitely much more complicated than our machine learning class from last semester.
Yeah, it took a lot of time for me to digest those papers as well. I guess I'll quickly mention that I said VRNN is built upon recurrent neural network, and there's another concept that's also inspired this VRNN. It's called variational autoencoder. For the you probably know, yeah, for the autoencoder it had this latent space Z that you do. So for regular autoencoder, you have encoder and then you have decoder. But the middle, when you encode the data, you are doing a deterministic encoding. But with variational autoencoder, you are doing a sampling when you're doing the. Either view VRNN as a variational recurrent neural network, or you can view it as a VAE with a time component in it. Yeah.
Yeah, that's actually a really cool connection. That makes a lot of sense.
VAE is more commonly introduced now. We did cover it in the machine learning as well. Yeah. Medical imaging. I think medical imaging would work because here we're essentially doing on satellite image data. So I wouldn't see why it won't work. Yeah, I personally haven't worked with medical imaging data, but I think it would be cool to try.
Well, it looks like I don't think we'll have more questions coming in, so we'll probably give people
some break time.
Yeah, 5 minutes before we go into the stage area. So do stick around if you can. We'll have more networking session later, and we look forward to getting to know you. And thank you so much, Flora, for an awesome presentation.
No problem. It was a pleasure. Thank you for inviting me, Kim. All right. I'll see you in the large session.